Hi, everybody. Welcome to Lecture 6. Before we jump into the very last exciting part of the lab instrumentation area that I'm always I love this part. I want to send out a little quick reminder that we're about to jump into Chapter 6, which deals with how to look at molecules and how molecules actually appear to each other in three-dimensional space. So please, if you can, before you take a look at Lecture 7, here's a little quick reminder, please try to build 2-butene. We're going to be looking at that molecule in particular and how it appears in three-dimensional space. And so it'd be great if you could build that molecule before watching Lecture 7. All right, now let's step back to, let's see, NCIS. Abby, remember?
Jackpot. It's Major MassSpec calling. Oh, I love this machine.
I love this machine too. This machine is awesome. So MassSpec is one of my favorite instruments for two reasons. One is that we have access to it in our actual chemistry labs, and therefore it's a unique piece of instrumentation that very few undergrads get to play with. And we play with it a lot. So you will see it a lot throughout our labs, even remote labs. I'm going to introduce mass spectrometry in our remote labs a lot, just so that you get a handle on it. The other thing that I want to make sure we're clear about is how this mass spectrometer works. And so it'll help you understand what the data is that you're looking at and how to analyze it. So instead of me explaining it in detail, I thought I'd let somebody else do it. So take a second to listen to this really interesting description. I love the little echoey voice as it goes along. Maybe it's catchy to you too, but check this out.
While chromatography separates compounds depending on their chemical and physical properties, mass spectrometry, or MassSpec as it is commonly known, reveals a compound's molecular weight. In a mass spectrophotometer, a beam of electrons bombards a single chemical sample with enough energy to break apart molecules. The fragments produced are propelled through a magnetic field and automatically sorted according to their mass and charge. An ion detector collects and records the fragments, producing a graph showing the mass-to-charge ratio of each. To analyze the information and deduce the structure of the original molecule, a scientist must work backward, reassembling the fragments on paper. When all goes well, they fit together like puzzle pieces to reveal the composition of the original sample.
Beautiful. Sounds easy enough, right? So just to give you now a cartoon version of what was just described, let's be really clear about the chaos and literal destructive process that this instrument is doing. That electron beam that is blowing apart your molecules, really, its job is to take a full molecule, a nice happy molecule like M, and this electron beam is very high energy, and so it can bounce an electron off of your entire molecule and leave your molecule missing an electron, but remaining essentially intact. So there are a few molecules that can get through our instrument that only have one electron ripped off of them, and therefore the whole molecule is still there, and we can measure its mass. And if its charge is +1, because it just had one electron ripped off of it, then really what you're measuring is its molecular weight, because an electron doesn't weigh anything. So this is the most important piece of information that a mass spectrometer will be able to give you. A mass spectrum, or an MS, is what we abbreviate it as. The data that is most critical to you will be the molecular weight. Now, let's take a look, because again, this is a very destructive process taking place over here. And there's nothing that says that this electron beams that are hitting your molecule do not blow up your molecule into other ions lighter than what the molecular weight is, okay? So here's an example of our favorite poster child of toluene. And when methylbenzene has an electron shot at it, it is true that yes, one electron can come off and you get the molecular weight, which we will now call M+. Like it was really hard to put a W there. So in everything in chemistry, we like to abbreviate things. We've abbreviated MW down to M. Okay, so M+ is the molecular weight, and for methylbenzene, the molecular weight is 92 grams per mole. Okay, we'll talk about in a second why you don't see a decimal here, why it isn't like 92.156 grams per mole. You will never see decimals in any of the masses that you get from your mass spectrometer. Very important. I'll let you think about why that might be the case, and then we'll answer it in a slide. But since this molecule is being thrown in and there's tons of these molecules being put in, and the instrument can detect every molecule, not every molecule is just going to have one electron ripped off of it. Some of the molecules will actually be blown apart. And the easiest place to break a molecule is between a sigma bond, 2 electrons single bonded. That is the easiest place for an electron beam to come in and boom, blow this molecule apart. And you can see it creates these interesting little species that only have 1 electron dot on each end because it actually cleaved the bond in the middle. What we will be looking at is this heavier piece, never to see the lighter piece, but we'll look at the heavier pieces and notice we'll also see this 77 mass show up in our mass spectrum. And therefore, sometimes we will see the heaviest piece as the molecular weight, but oftentimes, as you saw in the movie, there are smaller masses and smaller peaks that show up in a mass spectrum, and these are all called fragments. Kind of a good name for a destructive process. Boom, it blows apart into bits and pieces known as fragments. And so it's these fragments plus the molecular weight that might help us deduce the structure of an actual unknown compound. But again, keep in mind, the most important piece is this molecular weight here. That's what we really want to get from our mass spectrum. Okay, so I want to be really clear here now about this molecular weight. Here is what a mass spectrum will look like. Notice there's an 86 here. I automatically give it M+. It's the heaviest mass in my mass spectrum, and therefore it should be the molecular weight of my compound. This actually turns out to be the molecular weight of hexane, okay, C6H14, I think. So this has a mass of 86. Why doesn't the mass spec show us a molecular weight that's, as I mentioned, some kind of average? If you were to go like Google the molecular weight of hexane, you would see a mass of 86.352 or some decimal number for every molecular weight. Even when you start playing around with the periodic table and using the carbon 12.01 and H 1.001, you know, these all have decimals up here. So even if you were to add it up yourself using the carbons and hydrogens from your own periodic table, you would get a decimal number. So why doesn't mass spec give us a decimal? That is the end all be all question. Why are these all whole numbers? And it is incredibly important. Here is why. Mass spec is Abby from NCIS's favorite instrument because it is actually measuring the mass of every molecule, one molecule at a time. This molecule, how much does this one weigh? This molecule, how much does this one weigh? Every single molecule that is injected into the instrument gets measured. So all of these numbers up here are based on the averages of the isotopes of all these atoms in nature. So for example, carbon is mostly carbon 12, About 99% in the world is carbon-12, and there's about 1% carbon-13. So the periodic table says that the average atomic mass of carbon is roughly 12.01. But what MassSpec is doing is it is going to measure all of these, and the majority of these are all going to be carbon-12s. What's the majority of hydrogen in nature? Yes, that's not a trick question. H1, again, tons of it. Very little H2, H3, very little other isotopes of heavier abundance. So we are going to do all our math, since we're measuring each molecule one at a time. We're going to do all the math for molecular weight based on the most abundant isotope in nature, carbon-12 and H1. And therefore, there should be no decimals. This is based on carbon-12 and H1. If you did the math and figured out 14 times 1, 6 times 12, you should come up with 86. Okay? Very, very cool. So it is a very sensitive instrument as well. And this is why Abby in NCIS loves to use it to detect even the trace small amount of blood or drug or compound in any mystery case. And this is why it's a very popular tool in forensic science. Okay, cool. Now, the world is not made up of just carbon-12 and H1. So other isotopes in nature and other atoms are a little unique. Bromide, chloride, and nitrogen have some unique properties about them, and they will allow us to see them easily or easier in a mass spec compared to an IR or a carbon NMR. Okay, so let's go take a look at these three. What is unique about bromide when we have a bromide on our actual molecule? Well, what I want you to notice here is that according to the periodic table, bromide and its major isotope, it's somewhere around 79.9. So maybe you're thinking that the major isotope in nature for bromide is Br80. Wrong. Oh my God, it's a mystery to me why it happens, but nature has decided not to have any Br80 in the world, none. That all of the Br in the world is 50% Br79 and 50% Br81. Oh my God. So really, when you get to mass spec, you will never see Br80 on any of your molecules and should never use Br80 to do any of the math for figuring out your molecular weights, and should never use the atomic mass given on the periodic table, which is an average of these two major isotopes in nature. Mass spec, since it measures every molecule, I put in 100 molecules that have Br on them. 50 of them will have a mass using Br79. 50 of them will have a mass using Br81. So it's very easy to spy bromide in our mass spec because it's measuring every molecule. And so if it measures every molecule, I can look for these peaks that are the heaviest molecular weight for this compound, for example, 1-bromohexane, and see that if I do the math with carbon-12 and H1 and Br79, I will get that all to equal 164. But then I want to do the math again with Br81, and you should notice that Br81 will give you 166, of course, 2 mass units heavier. So you get these cool little twin peaks, 2 mass units apart of equal height for your molecular weight, and it is a big screaming out here that this is a brominated compound. And you can even see when it fell apart a little bit. Some piece fell off of bromohexane, and it still has the Br on it. I know they're not equal height, but they're relatively equal, and they're 2 mass units apart. Is there anything on the periodic table that weighs 2 mass units? Hydrogen's 1, helium is 4. There's nothing that weighs 2. There's nothing that could fall off and go 2 mass units. So this is screaming out at you, Br, Br, Br is on your compound. And it is one less mystery to figuring out what's your molecule made up of. It has a bromine on it. So we love MassSpec for this. So the one little curious thing, if you want, and again, I've already got the molecular weight here. So this is the M plus, as you can see, and then we call M plus 2 when we play around with BR81. Just a definition, don't worry about it. If we want to see fragments that might work, I look at what had to fall off to get to 135 and 137. So from 164 and 166, I got to 135 and 137. In both of these, in both of these situations, I lost 29. 29. What weighs 29 in my molecule here? 2 carbons and 5 hydrogens. This is 29 grams per mole. So to get to this fragment right here, this molecule and some of the molecules that got injected into my mass spec must have been bombarded with electrons. Remember? Boom! Destruction! And very few molecules remained intact as a whole molecule, but a lot more fell apart and lost an ethyl group. CH2, CH3 fell off. Granted, this isn't just bonus info for us. It's okay if you don't actually see this, all right, or use this data. But it's bonus. And trying to figure out a mystery compound, we like as much data as possible to confirm our final structure. So this might be helpful. All right, let's go play with the other weirdo. Chloride, the other weirdo in the group, 35.453. Another weird decimal. Is it kind of like, it's not even, what? Okay, so here, I'll just skip to the punchline. The punchline is chloride is a mixture of 2 major isotopes, but not in a 1-to-1 ratio, but in a 3-to-1 ratio, where we have a lot more chloride 35 than we do chloride 37. So as you'll see in this mass spec, that this molecule must have chlorine in it because this peak is at 128, and this one is about 3 times larger than the one at 128, and they're 2 mass units apart. While I'm looking at that region, notice there's these little itty bitty peaks down here and here. And there's always little itty bitty peaks everywhere in our mass spec. Little 1 mass unit heavier, 1 mass unit lighter. These are all due to the other isotopes. Carbon 13, had to make an appearance in 1% of the molecules sometimes. So it's going to show up as little teeny peaks around your major abundant peaks that are all made with carbon 12 and H1. And in this case, chlorine 35 and chlorine 37. So then what I'd like you to do is, if it's a true unknown, can you figure out a possible formula that fits the molecular weight with a chloride attached here? Can you then take that formula and turn it into a possible structure that could fit this data? This is the game we're going to play. This is the mystery we're going to try to solve. And coming up at the end of this presentation, we will look at how you will not only have mass spec data to help you figure out this mystery, you will have IRs, you will have carbon NMR, and you will even have some acid-base chemistry on this unknown. So tons more data is going to be given to you to help you figure out what is the structure of this organic molecule, which could be an unknown drug, could be the cure for cancer, could be who knows what in our orgo world, the structure of the coronavirus. These are all things that could be deduced using instrumentation and are true mysteries to us. Okay, so that was stalling time to help you figure out a possible formula. So when I'm trying to figure out a possible formula, again, one of the things I might do is do CXHYCl and start with knowing that it's got to have some carbons and hydrogens. Sure, it might have other atoms like oxygens and nitrogens, but why make your life harder? Start with just C and H and the Cl35 and see if you can come up with some formula that fits 126 with chlorine 35. And so what I did is I found one that is C7H7Cl35. And that matches my molecular weight of 126 grams per mole. Double check that math for me. I think that matches. So now I have to come up with a structure. Structure determination, when you have a formula, it'd be really great if you could go back to degrees of unsaturation and take this formula and figure out how many DUs have to be in your structure so that you just don't start drawing out, you don't start drawing out nothing but just alkane chains, because maybe there's a double bond, maybe there's a ring, maybe there's, how many DUs are there? And so when I stick this into my DU equation, I end up getting a DU equal to 4. If you have a DU of 4, there is a functional group that is screaming out for a trial, and you should try it the first time around for your DU of 4. That's a big DU. That's a lot of unsaturation. This molecule probably has a benzene attached to it somewhere, because benzene has a DU of 4, 3 double bonds in a ring, 4 DUs. So this is the structure that belongs to this molecule. Did any of you come up with this final structure as a possible structure? You could have come up with something else, as long as it had the correct mass and the correct pieces and the correct DU. 4 double bonds maybe in a chain, triple bond and a couple double bonds. As long as you don't have any 5 bonded carbons, you're in business, okay? And that's how we're gonna start using MassSpec along with all the rest of our data to try to identify unknowns. It's so fun. It's like a puzzle, and we all love puzzles, right? So last little weird atom that could make itself apparent to you in MassSpec besides chloride and bromide is nitrogen. If you have a nitrogen in your molecule, then nitrogen only has 3 bonds to it. And therefore, for example, NH3 has the major isotope of nitrogen is 14 plus 3 hydrogens. The molecular weight of this one is 17 grams per mole, an odd number. But notice if I start making CH4, I replace the nitrogen with a CH, I get a molecular weight of 16 grams per mole. It becomes even. So start to spy your heaviest mass, and if the heaviest mass is an odd number, it's very likely that it is a nitrogen in your structure somewhere, and you should start playing around with it and determining something like this with your formula. Can you figure out what happens with this formula? Which I'll post in just a second as well. Big warning right here. Big warning right there. Notice from the last one, there's lots of odd masses for fragments because these are little pieces of molecules. So an odd massed fragment does not mean nitrogen. It is only for the M+. Okay? And therefore, if it's only for the M+ and this has a 73 for its molecular weight, start with this idea of CXHYN. And for class today, see if you can come up with a formula, a DU, and maybe even a structure. That could fit this actual mass spec of a compound that has a molecular weight of 73. Okay? And then it's only a possibility. There could be lots of possibilities, but I'm really curious for class, what could you get here? Okay? Cool. Having fun yet? In summary, the most important thing you can remember about mass spectroscopy is that when you stick your sample into this instrument, it is measuring the mass of every molecule. And that means it's a very sensitive instrument. Notice this is the abundance on this mass spec. And therefore, what it's really showing you here is that there are about 6,000 molecules that remained intact and gave you a molecular weight of 136. That's amazing. It's counting the exact every single molecule and how much every single one weighs. And therefore, I can use only these isotopes from nature because these are the most abundant. So please do not use your periodic table. Do not Google molecular weights. Do not Google final answers for your structure because those molecular weights will not be true. Use these. All right? All right, let's go play. So let's go put it all together. You've had several classes now on IR, carbon NMR, mass spec. How do we put all this together? So this would be a similar problem that could happen to you. You could be given 3 pieces of data and asked which one of these above best fits all the data that you see below. So please try this for class. Please come to class with an actual answer that you can actually try to justify to your study group members. Okay? Let's play some more. Here's the other type of question you could be given, which is much more related to what we're going to do in lab tomorrow, is that lab 2 is going to be giving you all sorts of information like this about a specific unknown compound. And what I'd love for you to do is to use all of this data, including now some acid-base solubility data, that according to this unknown, it doesn't want to react in NaOH base, strong base. It doesn't want to react in a weak base. It doesn't want to react in an acid, and it doesn't even want to dissolve just in water alone. This is helpful information about this compound and the functional groups that could be on this compound. And that's important because remember, IR is about telling you kind of what possible functional groups. So please also use your literature table for the IR and bring it along to, laminate it, have it with you, and use it to help try to figure out a possible structure for this compound for class. Okay. This is the last one. Again, similar to lab, the more we play with this, the more data we see, the more puzzles we solve, the easier it'll be to do these puzzles. And so I'd really love for you to try these and see what happens, and we can talk about what you come up with in class. All right. Woo, the puzzle solving is about to begin. I'm very excited. I love lab 2. It's all about trying to get an unknown compound with all this data and seeing if you can figure out what it is from a list of possible compounds, but a long list of possible compounds. So please, again, feel free to ask for an appointment to Zoom in with me if you want to go over any of this on a one-on-one basis. I'd be glad to do that. Don't feel that you have to wait till study group to ask all your questions. I can meet you one-on-one, and definitely feel free to go meet with the tutors. Tutors rock. All right. I'll see you soon. Hope you're having a great day. Bye.